Welcome back. This will be a video lecture on section 3.2 of the text, Matrix Algebra. And in this section, we'll be studying the matrix algebra, or the algebra of four different matrix operations: addition, scaling, I'll treat that as one subsection, matrix multiplication, and then transposition. So let's begin with the algebra of addition and scaling. Now, the algebraic properties of matrix addition and scalar multiplication are contained here in Theorem 3.2, and these will look very familiar because they are essentially the same laws that we saw governing vector addition and scalar multiplication. So this should look very familiar. Throughout this theorem, we're going to let A, B, and C, capital A, B, and C, stand for some matrices of the same size, and little c and little d will be scalars. So let's just go through these laws A through H and just comment briefly on each of them. Law A is the usual commutativity law for matrix, in this case for matrix addition. It says I can add the matrices in the order A plus B or in the order B plus A, and it doesn't matter. I'm going to get the same result either way. Law B is the usual associative law. It says, suppose I'm adding the matrices A plus B plus C. On the left, I'm first adding A and B and then adding C. And on the right, I'm first adding B and C and then A. And what the associative law for matrix addition says is it doesn't matter. You're going to get the same result either way. Law C is talking about the existence of, well, we know of the existence of the zero matrix, but this is highlighting the property of the zero matrix. It says, when I take a matrix and add the zero matrix to it, it leaves it unchanged, all right? So that's the property of the zero matrix, that it leaves a matrix unchanged under matrix addition. Property D talks about the existence of what you might call an additive inverse. It says, for every matrix A, there's a matrix that when added to it, reduces it to the zero matrix, right? And that is what I get by scaling the matrix by a -1. So negative A is what I get by scaling the matrix A by -1, and that's acting as an additive inverse to the matrix A, all right? Very useful in solving equations, right? Because it allows me to eliminate a matrix on one side of an equation by adding its additive inverse. Okay, now there are two different distributive laws. One is, let's look at this first one, Law E. This is distributing a scalar over matrix addition. So if I have a scalar times a sum of matrices A and B, I can think of distributing that scalar over that matrix multiplication and rendering it as C times A plus C times B. But there's also a distributive law of a matrix over scalar addition. So if I have C plus D multiplying a matrix A, I can distribute the A, the matrix, over that scalar addition and write that as C times A plus D times A. Now, again, both of these distributive laws are going to be most useful as far as we're concerned kind of in this backward sense, more like a factoring law, right? It says if I see 2 times A plus 5 times A, I can think of that as 7 times A. And if I see 2 times A plus 2 times B, I can think of that as 2 times A plus B. So often these will be most useful as factoring laws rather than as distributive laws, but we'll state them as the distributive laws in E and F. Okay, Law G is similar to a law that we saw for vectors, and this is kind of what you might call a double scaling law. It says if I take a matrix and scale it first by D and then again by C, I can think of that as a single scaling of that matrix by C times D. So 2 times A followed by another scaling of 3 is equivalent to scaling once by 6, if you will. All right. And then finally, in Law H here, this is not saying much, it's just alerting us to the prominence of the scalar 1. It says, when I scale a matrix by the scalar 1, it leaves the matrix unchanged. So scaling by 1 leaves the matrix unchanged. Now, I want to prove one of these with you. I want to go to the document camera and we'll look at the proof of one of these. And so I've picked out Law E as one that's worthy of a closer look. So let's go to the document camera. We'll work out the proof of Law E. I would encourage you to work out the proofs of the others. and kind of satisfy your curiosity about them. And so join me at the document camera. Let's work out the details for E. All right, welcome to the document camera. We're going to prove law E of theorem 3.2, and it's effectively the distributive law of scalar multiplication over matrix addition. So C times the matrix A plus B is CA plus CB. Now, we'll use the following conventions throughout. We'll assume that the matrix capital A has generic entries little aij, and we'll assume that the matrix B has generic entries little bij. And what we're going to do, and there's many ways we could do this, what we'll show is that the entry in row I and column J of this matrix on the left is the same as the element that sits in row I and column J of this matrix on the right. So we just have to work out the ij entries of the left and the right hand sides and show that they're equal to each other. Now, the first thing we should do, let's work on the left hand side. The first thing we have to figure out is what is the ij entry of A plus B. And the rule for matrix addition is very simple. It just says the ij entries add. So the matrix A plus B is composed of elements or entries of the form aij plus bij. I simply add entry-wise or element-wise, and that's the matrix addition. Now, what is scaling going to do? It's going to scale all of the entries by the same factor of C. So if we ask for the ij entry of this matrix on the left, what's the ij entry of that matrix? It's simply going to be what I get by taking the ij entry of the matrix sum and scaling it by a factor of C. Now, just to facilitate our proof, let's just use the distributive law for normal real number arithmetic and write this as C times aij plus C times bij. And we'll stop there. That is a way of expressing the ij entry of this matrix on the left. Now, let's do a separate argument. Now, let's work out the ij entry of this matrix on the right. Now, what we have to do is we have to do two steps. First, we have to ask, what is the ij entry of C times A? And the scaling law just says that all of the entries of the matrix A get scaled by the factor of C. So that's simply going to be CAij. And we could ask the same question about this matrix. Right? What is its ij entry? But again, by the scaling law, when I scale a matrix by C, it scales all the entries by C. So the ij entry of C times B is simply going to be C times the entry in row I and column J of B. So we get that. Now, what is the ij entry of this matrix sum now? All right, let's work that out. So if I take CA plus CB and I ask for its ij entry, well, matrix addition says I take the ij entries of each of the constituent parts and I simply add them together. So it's going to be CAij plus BCBij. And what we notice after all of this is that the ij entry of the left and the ij entry of the right are equal to each other. So these pieces are equal. And since these matrices are equal in every single element, right, for every I and every j, we say that the matrices are equal. All right? So we've shown that both the left and the right-hand sides have exactly the same elements in row I and column j. Therefore, the matrices are equal. So that's a typical way that we can prove, in fact, all of the laws in Theorem 3.2. So I'm going to encourage you to work out some proofs for yourself and satisfy your curiosity about Theorem 3.2. All right, let's return to the class notes and continue. At the level of addition and scaling, there's an incredible resemblance between matrices and vectors. In particular, one of the ideas that we studied with vectors was the idea of a linear combination. And that idea persists here with matrices. So take a look at these matrices here. These are a collection of 2x2 matrices. I've got an A, a B, and a C. It makes perfect sense to think of scaling this matrix by some scalar little a, scaling this by some scalar little b and scaling this by some scalar little c and then adding them together and then asking whether or not I can contrive some choice of scalars so that that linear combination produces this matrix H, so that we can ask the same kind of question that we did for vectors. In this case, is the matrix H in the span of the collection of matrices A, B, and C? So join me at the document camera. I'll show you how to set this problem up, and we'll see that it's essentially the same, ultimately the same kind of problem that we've already worked with vectors. Welcome to the document camera. The problem before us is to see if we can combine A, B, and C, form a linear combination of A, B, and C to produce H. So we know in principle what we have to do is look for some coefficients. Let's call them alpha times A, beta times B, and gamma times C that would produce this matrix H. If we can do this, then H is in the span of A, B, and C. If we can't solve this equation for alpha, beta, and gamma, then H is not in the span of A, B, and C. So let's think about what this means. We're going to scale this matrix by alpha, scale this matrix by beta, and scale this matrix by gamma, and we'll set it equal to H, and that should provide us with some equations. When we compare entries, it'll provide us with some equations that will bind alpha, beta, and gamma together. Let's take a look. So alpha times A reduces to alpha 0, 2 alpha, alpha. Beta times B will be minus 2 beta, 3 beta, beta, and 2 beta. And gamma times C will be minus gamma, gamma, 3 gamma, minus 2 gamma. And this is supposed to equal the matrix H. Now let's do, you don't have to do this next step once you get really proficient in this. You wouldn't have to do this intermediate step, but what I want to do is write this as a single matrix on the left-hand side by adding element-wise or entry-wise. So we'll end up with a single 2 by 2 matrix on this side. Its first entry is going to be alpha minus 2 beta minus gamma. That takes care of all of the first entries here, the 1, 1 entry, so to speak. Then we'll do the 1, 2 entry, so 0 plus 3 beta plus gamma. Then we'll have in this 2, 1 position 2 alpha plus beta plus 3 gamma. And then finally in the 2, 2 position we'll have alpha plus 2 beta minus 2 gamma. And we're wondering if we can find alpha, beta, and gamma to make this equal negative 10, 10, 12, negative 5. Can we choose alpha, beta, and gamma to do this? Now, what does it mean to say that this matrix is equal to this matrix? It means that entry by entry, they're equal to each other. So this is going to give us a system of equations, right? Just by comparing an entry on the left with an entry on the right. So our first equation, which we'll get by comparing these two entries, is going to be alpha minus 2 beta minus gamma equals negative 9. That takes care of those two. Let's go to this entry. 3 beta plus gamma equals 10. So that's comparing these two entries. 2 alpha plus beta plus 3 gamma is equal to 12. That's comparing these entries. And then finally, alpha plus 2 beta minus 2 gamma equals negative 5. So here's our system of equations that comes from this relationship between the matrices, right? This linear combination forming the matrix H produces this system of equations. Now let's put this in augmented form. And we'll remember that our columns correspond to alpha, beta, and gamma. We'll have to remember that at the end of the day. But right now we've got this augmented matrix. And just for future reference, it might be helpful to think about how the matrices, how did the information in the matrices end up in this augmented matrix? Is there a way that we could understand how to go directly from the matrices and the spanning question to our augmented matrix? And if you stare at this, hopefully you're seeing some interesting relationships, right? So if I take the entries of this first matrix and list them in this order, this, then this, then this, then this, kind of zigzag your way through this matrix, you see that that's right here. This is the first column, right? This first column contains the entries of the matrix A in that specific order, right? Now, if I take the entries of B in exactly that same zigzag order, I can see them listed here. Here are the entries of C, and here are the entries of H. So the matrix A, B, C, and H, they're appearing here in column form, right? So it's as if we're taking the rectangular form, or the square form in this case, and representing the entries in column form. So we're basically turning a matrix into a vector. Now, it's a fair question. I imposed a specific ordering to work our way through this matrix, kind of in a zigzag pattern across the first row and then across the second row. Could we have worked down, right? Could we have gone from down the columns instead? And that would be equivalent to just having these rows permuted. So we would be able to find an equivalence between those two systems, a system where you entered your matrices in column-wise rather than row-wise. That would correspond to just doing some row switches down here on this system, and that would produce an equivalent system. It's going to have exactly the same solution set. So the main thing is, when you want to go from the, when you're working on a spanning question, you want to go directly from the matrices to this augmented form, the answer is just to develop some kind of systematic way of working your way through the matrices and list all of the matrices in column form down here in your augmented system, and you can go directly from the matrices to this augmented matrix form. Okay, so you can kind of save yourself a little bit of work here and go directly to this augmented form. All right, now we still have to, there's still some work to do. Now, I went ahead and did this using the assistance of a computer, but you have to row reduce this now. All right, and this could easily be done by hand. I just wanted to save myself some time, but I went ahead and row reduced this, and I got the final form looking like this. And everything hinges on this now, right? It turns out that this is in fact a 0. All right, and that's good news because it says our system's consistent. This is not an inconsistency. And moreover, if we remember that this is alpha, beta, and gamma, this is telling me that alpha is equal to -1, beta is equal to 2, and gamma is equal to 4. And so the answer is yes, H is in the span of the matrices A, B, and C. And we can be actually quite explicit. We know that H, in fact, will be what I get when I take a -1 times the matrix A, 2 times the matrix B, and 4 times the matrix C. And you can check that out. If you take these matrices and combine them in this way, you will, in fact, recover the matrix H. So H is in the span, and we can produce the literal the set of coefficients that will give us a linear combination of A, B, and C to produce H. All right, very good. So hopefully we've learned a couple of things that the same questions that we were asking about vectors works for matrices, and there's a way in which there's a level at which we can basically think of these matrices as acting as column vectors in the spanning problem. Okay, now what I want us to do is go back to the class notes and take a look at another problem that's in the same vein. Well, let's continue with this theme. Are the matrices A, B, and C listed here, are they linearly independent? So join me at the document camera and we'll explore the independence of these matrices A, B, and C. All right, welcome to the document camera. The problem before us is to test whether or not this collection of matrices are A, B, and C linearly independent. And we know in principle what to do. We want to look to see if I can form a non-trivial combination, linear combination of the matrices A, B, and C. So is it possible to find a solution in alpha, beta, and gamma to this question, right? Can I find non-trivial alpha, beta, and gamma such that this linear combination is the zero matrix in this case, right? If we can, then the matrices are linearly dependent. But if the only solution to this homogeneous equation is alpha equals 0, beta equals 0, and gamma equals 0, then in fact these matrices are linearly independent. So everything hinges on how many, what's the variety of solutions that we have to this system of equations or the corresponding system of equations. Now, let's think about the augmented system that's associated with this, right? We learned in our previous solution that we can basically treat these matrices as columns if we just fix an order in which we read through them. And I'm going to read through them in this kind of zigzag order. We can basically treat these as column vectors. And so this question boils down to this in the augmented form. That matrix is going to go in as 1, 0, 2, 2, 1, 1, negative 1, 4, and 1, 2, negative 3, 7. Now, you can include the column of zeros on here or not. It doesn't matter because it's a homogeneous system, so nothing's going to change in this column. So you can include it or not include it. It doesn't matter. But this would translate into this system of equations where the columns represent alpha, beta, and gamma. And now you'd have to go through the task of row reducing this. Well, I did this, all right? I row reduced this. And you end up with the final form. There's a sequence of elementary row operations here that has to be done. That's not changing at all. But we end up with a 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. Okay, so that's our final augmented, our reduced row echelon form. And we can see that there's always going to be a solution to the homogeneous system of equations. But this one in particular says that since there's no free variable, right, alpha is equal to 0, beta is equal to 0, and gamma is equal to 0. And that means that the only solution to this equation is the trivial solution where they're all equal to 0. And that means that A, B, and C are linearly independent. Okay, so the only solution is the trivial solution. That is the meaning of linear independence. Okay, so let's head back to the document camera. We're going to see these same matrices reappearing in our next problem in a slightly different context. So let's head back to the document camera, or head back to the class notes and look at that problem. I want to do one last problem in this theme. In this problem, I want to describe the span of the collection of the matrices A, B, and C. So join me at the document camera for the solution to this problem. All right, welcome to the document camera. The problem before us is somewhat ambiguous. Describe the span of the matrices A, B, and C. Now, these are the same matrices we saw in the previous problem. We know that they form a linearly independent set, and now we would like to know, is there a way to describe all the matrices that we could reach by forming linear combinations of A, B, and C? So we're looking at things like this. Could I take alpha times the matrix A, beta times the matrix B, gamma times the matrix C, and form some matrix, let's say with entries X, Y, Z, and W. And if we could form them, what conditions would there be on x, y, z, and w? What kind of constraints are there on x, y, z, and w in order for this matrix to be in the span of A, B, and C? Now, one way to think about this is to look at the corresponding augmented system. Let's take a look at that. I'm simply going to feed the matrices in my usual zigzag way. And so we know that we can find an alpha, a beta, and a gamma to solve this system as long as this system is consistent. And so the real question is, what are the conditions on x, y, z, and w to make this system consistent? That's the question. When is this system consistent? When it's consistent, I can solve this equation and this matrix is going to be in the span. When the system is inconsistent, that means that somehow the x, y, z, and w are configured in such a way that I cannot reach it by forming linear combinations of A, B, and C. All right, so when is the system consistent? Now, the problem you're going to run into is, for instance, if you're trying to use something like the Linear Algebra toolkit or most systems, is that they won't let you work with a set of unknowns in this column, because you want to just row reduce this now and see what conditions are forced here in the last row. I'm going to have a row of zeros. We know that from the previous problem. I'm going to have a row of zeros on this side, and there's going to be some equation in x, y, z, and w on this side, and that's going to force the consistency question, that whatever's appearing in this position on the other side in that row reduced form is going to have to be equal to 0 for the system to be consistent. But most computer systems are not going to work with a column of unknowns and know how to treat that. So here's what I did. I wanted to employ some technology to help me do the row reduction, but I knew that I couldn't work with this column of unknowns. And so what I did is I just performed the row operations on the coefficients with the idea that I would keep track of all my steps, and then I would apply them to the column of constants here on this side, the x, y, z, and w. So here's what I found. I found that this matrix of coefficients, and we saw this in the previous problem, the matrix of coefficients alone it row reduces through a sequence of several steps to this matrix. Okay, so there was a sequence of row operations that I performed using the Linear Algebra toolkit to get me from here to here. Now what I did is I kept track of all my steps. And now what I'm going to do is perform those exact same steps on this vector x, y, z, w. And by the time I'm done doing all of those same steps just to this column, I can basically just assert that if I augmented this with the column x, y, z, and w and take my final vector that I get after I do all the row steps on it and tack it on here, that will be equivalent to have done all the row steps on the augmented system all along. All right, so what I found is that when I went from here to here, the row steps that I did, they broke down into 3 major types. I used row 1 to affect some changes, I used row 2 to affect some changes, and I used row 3 to affect some changes. So I had 3 major types. I was just using these same type 3 operations all the way through. So in step 1, I did this sequence of steps. I used row 1, so I did -2 times row 1, and I added that on to row 3. I did -2 times row 1, and I added that on to row 4. In step Roman numeral 2, I was using row 2. So I was using row 2 consistently here to affect changes in rows 1, 2, and 3. And then finally in step 3, I used row 3 to affect changes in rows 1, 2, and 4. So I had 1 times row 3 added onto row 1. And I used a negative 2 times row 3 and added that onto row 2. And then I think, yes, I did negative 1 times row 3, and I added that onto row 4. So these were the changes that I did to bring this matrix of coefficients down to this row-reduced echelon form. I'm going to do the same steps now in exactly the same order on my vector x, y, z, w. So when I do the changes in this first sequence I'm using a negative 2 times row 1 and adding that onto row 3. So row 1 is not changing. Row 2 is not changing. I'm taking a minus 2 times this and adding it on to row 3. So that's going to be z minus 2x. And I'm doing the same thing. I'm taking a negative 2 times row 1 and adding it onto row 4. So w minus 2x. So that's how things look after that first set of row operations. Now I'm going to go to my second set of row operations using the row operations described here in 2. And now I'm using row 2 to have an effect on 1, 3, and 4. So row 2 is not changing. That's just going to simply be y. But now what am I doing here? I'm taking a negative 1 times row 2 and adding it up onto row 1. So that's going to be x minus y. I'm taking 3 times row 2 and adding it onto row 3. So that'll be z minus 2x plus 3y. And then I am doing a negative 2 times row 2 and adding it onto row 4. So that'll be w minus 2x minus 2y. That's a minus 2y there. Okay. Now, I have to highlight this because this gets a little... In this last step, we're using row 3 to change rows 1, 2, and 4. So let's really be meticulous here. Give ourselves some space to work. All right, I'm going to take 1 times this row 3 and tack that on to row 1. So I'm going to have the original x minus y, and then I'm going to have 1 times this being added on. Okay, that takes care of that operation. Now I'm taking a negative 2 times this row 3 and tacking that onto row 2. All right. Now row 3 is not being changed, so I'm going to leave that in there. Now in my last operation, I'm taking a minus 1 times row 3 and tacking that onto row 4. So I'll have the existing row 4. Right, that's the original row 4. Now I'm tacking on minus 1 times row 3. All right, and I just broke through the barrier of my vector here, so I didn't give myself enough space. Now I'm going to clean this up. So I'm not doing a row step here. I'm just trying to clean this up a little bit, right? Now, when we look in this first entry here, we've got x, we've got a minus 2x, so that's just a negative x. Let's look at the y's now. I've got a minus y, I've got a plus 3y, that's a plus 2y. Let's look at the z. I've just got the single z and no w, so I just have a plus z. And so that simplifies that first entry. Now let's look at this next entry. Let's look at the x first. We've got no x's here. I've got a plus 4x, so 4x. Let's take care of y next. I've got the y, and I've got a minus 6y. That's a minus 5y. Let's take a look at the z, a minus 2z, and there's no w, so minus 2z. Okay, third equation is already in pretty simple form. I'll just write it kind of in a natural ascending order, so I'll just write that as minus 2x plus 3y plus z. And then finally, and this is the one that's actually most important for us, let's get this one right now. How much x do we have? We've got a minus 2x here, but because I'm distributing the negative 1, I'll have a plus 2x here, so there's going to be no x. All right, so the x's are taken care of. Let's look at the y's. A minus 2y, and by distributing that negative 1, so that'll be a minus 5y. All right, so that takes care of the y's. Now let's take a look at the z. I've got no z here. I've got a minus z, so I'll have a minus z. And then finally, the w's. I don't have any w here. I've got a w there, so plus w. Okay, so this is, let's make sure we understand what's going on here, just because we may have lost the big picture by going into this kind of fine-grained analysis here. Here's what I'm suggesting. Had we started with this augmented system, right, and followed these exact same steps, we would have ended up with this matrix here, right? That would have been on the left. That would have been augmenting this. We would have had this matrix on the left augmented by this matrix on the right, or this vector on the right. And so what is this telling us? The question of consistency boils down to, is this row equal to 0? Is this element equal to 0? Because in order for the system to be consistent, this row of zeros has to be paired up with a 0 on this side. So the system is consistent provided that this minus 5y minus z plus w is equal to 0. In other words, if someone hands you a matrix, if they hand you a matrix and they ask you, tell me whether this matrix can be spanned by A, B, and C, all you have to do is pull out the y, the z, and the w, put them into this equation, and see if it's true, right? If this is true for the x, y, z, and w that are in that matrix, then it can be spanned. If this equation is not true, then it's not in the span. So this is what we mean by, right? We're trying to like add some meaning now. Retroactively, we're saying, what did we mean when we said describe the span of A, B, and C? What we're saying is, I can give you a very simple test on your matrix to see whether or not it's in the span of those other matrices. I'm just going to check this equation. If it meets this equation, it's in the span. And if it's not in the span. Now, in fact, we get more than this, right? We've only used this last entry, right? When this is true, this gets zeroed out, and we're going to be able to take the other elements in our matrix, and we're going to be able to calculate values for the first, second, and third entries. And those are going to correspond to the values of alpha, beta, and gamma that will combine to produce the matrix in question. So when a matrix is in the span, when it meets this condition, I'll also know the coefficients that I can use to combine with A, B, and C to span to form the matrix in question. Okay, so we actually get a lot more out of the work than just a description of the span. We also know how to choose the coefficients to produce the matrix that's purportedly in the span. Okay, that was probably as complex an analysis as we've done in a while, so I hope you enjoyed that. Let's head back to the class notes. We're going to turn our attention now to the algebraic properties of matrix multiplication. Now, these properties are contained in Theorem 3.3, and in the statement of this theorem, capital A, B, and C are going to be matrices. We're going to be seeing lots of matrix multiplication and matrix addition, and it's assumed that throughout the statement of this theorem that these matrices have sizes that are conformable for the operations that are indicated. So none of these are supposed to be nonsensical. K is going to stand for a generic scalar. All right, let's take a look at laws A through E and comment on each of them. So law A is probably the most interesting law that's in this list, and it's probably the hardest to kind of give a convincing proof of, and yet it's very, very important. It says, if I were to multiply three matrices together in the order ABC, from left to right ABC, I could think about that as first multiplying B and C together and then multiplying on the left by A, or I could think of first multiplying A and B together and then multiplying on the right by C. And the associative law says that it doesn't matter. That's going to produce the same result either way. So this allows us to write A times B times C without parentheses, and it has no ambiguity whatsoever. So I can simply write A times B times C, and no matter how you would think of processing that, you're going to get the same result. So that allows us kind of the freedom to not have to worry excessively about the parentheses in the associative law for multiplication. Now, law B is a distributive law. It's a distributive law of matrix multiplication over matrix addition. So on the left-hand side here, we're adding two matrices together, B plus C. Now those matrices, of course, have to be of the same size. Now A is multiplying that sum on the left. So this is A times the sum B plus C. And what this is saying is that that multiplication will distribute over the addition and allow us to write that as A times B plus A times C. Now, read in the other direction, it looks like a factoring law. It says we can factor the matrix A out on the left. Now, we have to be very careful because the one law that we're not going to see in this table is the commutative law, right? So we have to be careful, especially when we're factoring. If we see A times B plus A times C, we can factor the A out, but we have to respect the fact that the A is on the left here. So we can factor the A out on the left and write that as A times the sum B plus C. It would be wrong to try to factor the A out and write it on the right-hand side, because that would be we would be introducing a commutative law, which is not in effect for matrix multiplication. So if you're going to use this as a factoring law, you have to respect the side on which the multiplication is is being formed. In this case, A is on the left, so it needs to be factored out on the left. Now there is a right distributive law, so multiplication on the right also distributes. But again, if I'm going to interpret this as a factoring law, I have to respect the fact that the C in this case is on the right and needs to stay on the right even after I factor. Okay, so the lack of a commutative law is really coming into the fore here. We can see that we have to treat these distributive laws with some care because of that. All right, the second to last, law D is basically saying on the left here, if I form the matrix product A times B and think of scaling that by a factor of K, that I could just as well have scaled the matrix A by the factor K and then multiplied by B. Or I could have scaled B by K and then multiplied by A. Now, typically, this will be used, again, in a kind of a factoring form. So if I saw something like this, or if I saw something like this, I could think of kind of pulling that scalar out and doing the matrix multiplication first and then scaling the results. So typically this will be used in this factoring form. Finally, let's look at law E, and this is something that we hinted at with an earlier calculation, and this has to do with multiplication by an identity matrix, a matrix that consists of ones on the diagonal, and it's a square matrix, but a square matrix consisting of ones on the diagonal. And this is just indicating that there's an identity, there's an appropriate identity on the left by which to multiply the matrix A, and there's an appropriate identity on the right by which to multiply the matrix A. But no matter how we do that, as long as the multiplication is conformable, multiplication on the left or multiplication on the right by an appropriate identity will leave the matrix unchanged. Okay, now I want to do one of these with you. It would be grand to try to bite off the associative law, but I think that I'll have you kind of think about that on your own. Let's take a look at the document camera at law B here, the distributive law, the left distributive law to be precise. So join me at the document camera and we'll work out the left distributive law for multiplication over matrix addition. Welcome to the document camera. We're going to prove law B, or part B of theorem 3.3 on properties of matrix multiplication. And this is the left distributive law. So we have to show that if I add the matrices B and C first and then multiply by A, that's the same as multiplying A and B, multiplying A and C, and then adding those matrices together. Now, we're assuming throughout that the matrix addition and the matrix multiplications that we see are conformable. And so just to fix things, let's assume that B and C are both n times P matrices so that the addition makes sense. And in order for the multiplication to make sense, let's assume that A is of the form m times n. This way the middle entries, the n's match, and we know that the multiplication can be carried out. Now, a tried and true method to prove an identity like this is to show that the ij entry on the left is equal to the ij entry on the right. So these are both matrices. I want to show ij entry on the left is equal to the ij entry on the right. Now, the ij entry on the right is perhaps a little easier to calculate at first. So let's go ahead and work out the ij entry of the matrix AB. All right, so I'm going to take the matrix AB and I'm going to concentrate on its ij position. What is in the ij position of that matrix product? Well, we know in principle what to do. We have to take the row I of matrix A and dot it with the jth column of matrix B. A is on the left, B is on the right. So we're going to take the ith row of A and dot it with the jth column of B. So that's the dot product of these two vectors. And so that's going to produce something like, right, AI1 times B1J. We'll have AI2 times B2J. And this will go on until we get to the last elements. Okay, so that's going to be the element that sits in the ij entry of this product, AB. Now let's do the same for AC. The only change I have to make is now I'm using this row with this column. So it's formally going to look the same except with all the B's changed out for C's. All right, so that's the dot product of the row with that column. Now, that's the ij entries of these matrices taken separately, but we know that when we add these two together, that we're simply going to add the ij entries. And so what's going to be sitting in the ij entry of this matrix sum is going to be the sum of this and this. So we'll write that as so the ij entry of this sum on the right is simply going to be the sum of these things. Now, when I add these together, of course, I can factor out the common AI1, AI2, and the AIN. So this is going to be AI1 B1J plus C1J. That takes care of those two terms. Then I'll have the AI2 times a B2J plus C2J. And this will go on until I've exhausted all my terms except this last one. And then this last term is going to be AIN BNJ plus CNJ. Okay. Now, that's the right-hand side. Let's take a look at the left-hand side. When I add the matrix B and C together and I look at their IJ entry, right? The IJ entry, excuse me. When I add the matrices B and C together and I look at their jth column, it's going to be this. It's just going to be the sum of these two columns, right? So the jth column of the matrix B plus C is going to be this, right? So when I multiply A times the matrix B plus C, and I look at its IJ entry, I'm taking this row of A, that appears on the left, and this column of the matrix B plus C, and I'm dotting them together. So we're going to get AI1 times B1J plus C1J. That'll be the product of first elements. I'll have the AI2 times B2J plus C2J. That'll be the product of second components. And this will go on until I get to the end, AIN BNJ plus CNJ. So we can see that these two are exactly the same, right? The IJ entry of the matrix on the right and the IJ entry of the matrix on the left are identical, and therefore the matrices, since they agree in every position, the matrix on the left must equal the matrix on the right. And we're done. That's it. That's how we prove Law B. Now, all of the proofs for laws A through E in Theorem 3.3 will follow a very similar pattern. All right, so I would encourage you to try a couple of these just to get your hands on working some of these arguments in general. All right, let's head back to the class notes. All right, let's work a problem that requires us to reflect on all of these properties of matrix multiplication. So in this problem, A and B are going to be square matrices of the same size. And what I want to do is I want to multiply a pair of linear combinations of A and B. So on the left, I have 2A plus 3B. And on the right, I have 4A minus 2B. And what I want to do is use the distributive laws and the scaling laws to multiply this out and rewrite it. But I also want us to be aware that there is no commutative law for matrix multiplication. So that is going to affect how far we can go in simplifying this. So join me at the document camera and let's expand this product of linear combinations of A and B. Welcome to the document camera. We're going to use properties of matrix multiplication to expand this product of two linear combinations of A and B. So I've got 2A plus 3B multiplying 4A minus 2B, and we want to expand this and write it in a different form. Now, the one thing that I want to do is try to be attentive to the properties of matrix multiplication and scaling and addition that we're using as we work our way through this problem. So one of the things I want to do is first rewrite this part. So we can think of this as 2A plus 3B and 4A plus a minus 1 times the matrix 2B. So we should really think of matrix subtraction, or one way to think of matrix subtraction is an addition and a scaling by -1. Now we can use our double scaling law. We can think of this as minus 2 times, the scalar minus 2 times b. So let's do that. Okay, so we can think of that as a single matrix, minus 2 times b. This is 4 times a, 3 times b, and 2 times a. And now we just have matrix addition here throughout. Okay, now, the first thing we're going to do, and you could do this either way, I'm going to think of keeping the 2a plus 3b together and thinking of that as a single matrix that's multiplying this sum on the left. So I'm going to use my left distributive law. I'm going to bring this 2a plus 3b and I'm going to distribute it onto the 4a and onto the negative 2b over this addition. So we can write this as 2a plus 3b times 4a plus 2a plus 3b times minus 2 times b. Okay? And now I'm going to use a right distributive law to distribute the 4a across this matrix sum, and the minus 2b can be distributed across this sum. So now we're going to use the right distributive law. And so we're going to get a 2a multiplying a 4a, a 3b multiplying a 4a. We've got a 2a multiplying a negative 2 times b. And we've got a 3b multiplying a negative 2 times b. Okay, so those are we used a left distributive law and then a right distributive law. And now we just have to use properties of scaling. I know that I can combine the 2 and the 4 into a single scalar, namely an 8, multiplying an a times an a. And we can write a times a as a squared. Okay, that takes care of that term. Here I can combine the 3 and the 4 to give me a single 12. And I want to be careful here. I have to preserve this order. This is b multiplying a. b on the left, a on the right. So I'm going to write that as ba. I have the 2 and the minus 2, which will combine to a minus 4. So I've got a minus 4 multiplying ab. And then here I've got a 3 and a negative 2. That's a negative 6 multiplying a b times b, or a b squared. Now typically, I mean this is fine, but typically you won't see it written this way. We'll basically reverse the step that we did right at the beginning, and this will be written as, I'll show you. We'll usually write this as 8a squared plus 12ba minus 4ab minus 6b squared. So typically these negative scalars might be written as positive scalars with subtraction. Okay, now the point is I was trying to be very attentive to the various rules that we have for matrix multiplication, scaling, and matrix addition. But in truth, if we look at this, right, now that we've done this, if we look at this, we can basically just do our normal, we can multiply these as if they were binomials, right? We'll have the 2a and the 4a are giving me the 8a squared. The 2a and the minus 2b are giving me the minus 4ab. The 3b and the 4a are giving me the 12ba. And then the 3b and the minus 2b are giving me the minus 6b squared. So you basically can just multiply these out as if they were ordinary binomials. The one thing, a product of binomials, the one thing that you have to be attentive to, though, is the order in which the matrix multiplication is taking place. So when you do this outside term, it's really minus 4, a on the left, b on the right. And when you do this inside term, it's 12ba, b on the left, a on the right. The fact that we don't know, right? We don't know if BA and AB are the same thing. So we have to keep those products in the order in which they appear in the multiplication. And we cannot equate these two. So it would be wrong at this point to try to simplify these two by bringing them together either as BA or AB. So we have to leave it at this. This is as simple as we can make this, short of knowing something about BA and AB equaling each other. All right, so that's a good exercise in just taking some square matrices and showing how we can take these kinds of linear combinations and expand them, as it were, in this case. All right, let's head back to the class notes. Let's explore some of the algebraic properties of matrix transposition. Now, the properties of the transpose are contained here in theorem 3.4. And throughout this theorem, capital A and capital B will denote matrices, and K will denote a scalar. Now, we'll be seeing some matrix addition and some matrix multiplication in the list below, and we'll always assume that the matrices A and B are of the appropriate size for the indicated operation. All right, let's take a look at each of these laws one at a time and comment briefly on them. So law A says something that's fairly commonsensical, right? It says if I take a matrix A, take its transpose, and then take the transpose of that result, I get back to exactly where I started, right? If I take a matrix and I exchange the rows and the columns, and then I exchange the rows and the columns of that matrix, I am back to exactly where I started, right? So the transpose of a transpose is back to the beginning, all right? So a double transpose has no effect on a matrix. All right, law B says something interesting. It says, if I take a pair of matrices and I add them together and then take the transpose, that is equivalent to first taking the transposes and then adding the matrices together. So it looks like you could think of it as transpose distributes over matrix addition, right? That's one way of thinking about this. It's kind of a visual cue here. It says I can distribute the transpose over the matrix addition. Law C says something not unsurprising, right? It says if I scale a matrix and then take the transpose, that is equivalent to first taking the transpose and then scaling. That is not a surprising law, and I would encourage you to try to prove that for yourself. Now, the most unexpected result in this list is this rule for the matrix product. It says if I take a product of two matrices A and B and then take the transpose, that is equivalent to first taking the transposes but then multiplying the matrices in the reverse order. That's unexpected and that's surprising. We'll take a look at this one in detail under the document camera, so we'll get some level of comfort with this rule. But this is one you'll have to remember, that when you want to take the transpose and apply it to the underlying parts of a matrix product, you're going to have to reverse the order of the multiplication. All right, so remember that. Property E you can think of as an application of D. It says if I have a matrix A and I raise it to a power of R, and then I transpose that's equivalent to taking the matrix transpose first and then taking the power of that. That can be done very easily by repeated applications of law D. In particular, when R is equal to 2, this is just saying A times A transpose is equal to A transpose times A transpose, right? That is reading law D here with B equal to A. So E is just a special case of D. So the real interesting one here is law D. So let's head over to the document camera and explore the meaning of law D. Let's see if we can understand how this comes about. All right, welcome to the document camera. Our goal is to prove law D from theorem 3.4 governing properties of the transpose. And we're going to show probably the most surprising property of the transpose, which says A times B transpose is equal to B transpose times A transpose. So let's look at the proof of this. And what we're going to do is we're going to show that the ij element on the left-hand side and the ij element on the right-hand side are always equal. So we're essentially showing that every entry in the matrix on the left is equal to every entry in the corresponding position on the matrix on the right. So let's take a look at, let's start with this left-hand side. Let's think about what is the ij element. So we've got A times B. So we're first multiplying A and B, and then we're taking the transpose of that, and then we're asking for the element that sits in position ij. Now, we know that the relationship between the transpose and its underlying matrix, the element that sits in position ij in the transpose, is the same as the element that sits in position ji in the regular matrix. All right, the roles of the rows and columns have been reversed. So whatever is sitting in, for example, the 2-3 position in the transpose is what's sitting in the 3-2 position of the matrix itself. So we have this relationship. Now, let's think about what is involved in this calculation. If I want to find the ji element of the matrix A times B, I have to take row j of A and dot it with column I of B. That's what I have to do. I have to pull a row out of matrix A, and it has to be row j. I have to pull a column out of matrix B, and it's going to be column I. And I have to form the dot product of those two. Now, let's think about this. Row j of A is equivalent to column j of the transpose of A, right? Because the rows and the columns get interchanged when I go from the matrix to its transpose. So the jth row of A becomes the jth column of A transpose. The column I of B is the same as the row I of B transpose, because the roles of rows and columns get reversed when I go from B to B transpose. So the ith column of B is the same as the ith row of B transpose. Okay, now we know that dot product is commutative, and so I'm just going to reverse the roles of these. You'll see why. I think it looks nicer if I put row I here. I'm going to do row I of B transpose times column j of A transpose. Okay, that's that dot product. And now when I step back and look at this, this looks like the ij element of the matrix B transpose times A transpose. Right? Because if I was given this to calculate, I would take this first matrix and grab its ith row. I would take this second matrix and grab its jth column, and I would form their dot product. But that's exactly what we're seeing here. So through this process, we've shown that the ij element of AB transpose is the same as the ij element of B transpose A transpose. And since these two matrices are equal entry by entry, it must be that they're equal to each other. So we've been able to show this through this argument. Okay? So we're just making repeated use of the relationship between a matrix and its transpose, how the columns of one become the rows of the other, and the rows of one become the columns of the other. Okay? So it's not a difficult proof, but you have to kind of understand how a matrix and its transpose are related in this fashion. Okay, so let's head back to the course notes. I want to show you one more thing regarding the transpose. Let's close out this section on matrix algebra by looking at theorem 3.5. Part A says, if A is a square matrix, then A plus A transpose is a symmetric matrix. Part B says, for any matrix A times A transpose and A transpose times A are symmetric matrices. So let's head over to the document camera. I'll show you how we can prove parts A and B of theorem 3.5. All right, welcome back to the document camera. We're now going to prove A and B of theorem 3.5, and this is showing that some matrices are going to be symmetric matrices. Now, I'm not stating the entire set of hypotheses, so it's assumed that this matrix A is a square matrix, and this is assumed to be any matrix. Okay, so let's make sure that we understand how the proof of A works first. So what if I add a matrix A and its transpose? I want to show that that matrix is symmetric. Now, let's remember what it means for a matrix to be symmetric. It means B is symmetric if I take its transpose and I just return back to the matrix itself. So one way to think about how to prove a matrix is symmetric is to show that its transpose is just itself. So with that guiding principle, let's go ahead and take a look at this. I want to test the symmetry of this matrix by looking at its transpose. But let's remember that one of the important properties of the transpose is that, in a sense, it distributes over this matrix addition. So I can think of this as A transpose plus A transpose transpose. All right, so I can effectively distribute the transpose over this matrix addition. I won't do anything with A transpose, but I will remember that transpose undoes itself, right? So if I take the transpose of the transpose, I'm just back to the matrix itself. And now matrix addition is commutative, so I can write this as A plus A transpose. And that's exactly where we started. We've shown that if I take A plus A transpose and transpose it, I just get back A plus A transpose. Therefore, A plus A transpose is in fact symmetric. Okay? Now, before we look at this proof, and the proof is going to follow kind of the very similar vein, let's just make sure we understand what's going on with this multiplication and why is this always conformal? Why does this always conform to matrix multiplication? So let's think about what's going on here. We've got a matrix A, and the theorem says this can be any matrix, right? The size of this matrix is unspecified, and apparently it doesn't matter. Let's see why. So if, for example, if A is m times n, right? If it has size m times n, we know that when we take the transpose that the rows become the columns and the columns become the rows, and that means that the transpose is always going to have the size of the transpose will always be reversed. It's going to be n times m. Okay? And so it says no matter what we start with, no matter what matrix we start with, if I multiply on its left by the transpose, and the same argument would show if we multiply on the right by the transpose, that's always going to conform. The matrix product is always going to work. In this case, we'll end up with an n times n matrix. If we multiplied on the other side, we'd end up with an m times m matrix. So the point of this early part of this discussion is just to verify that this multiplication always makes sense for any matrix A. Now, what I need to show is that when I take the transpose of this, we're going to basically use this same idea here. When I take the transpose of this matrix, I want to show that I get back this matrix. Let's see why that's true. Okay, so one of our properties of transpose is how it works with multiplication, matrix multiplication. And if you remember, we take the transpose of these two matrices, but we have to reverse the order of the multiplication. So it's going to be A transpose times A transpose transpose. So those are getting reversed. The order in which they appear in the multiplication is getting reversed. Now let's use our fact that the transpose of the transpose is just the matrix itself. And so this is just A transpose times A. And that's exactly where we started, right? A transpose times A transpose is A transpose A. All right. And therefore, A transpose times A is symmetric. And that's all we have to show. All right. So I would encourage you to try to work this argument with the role of A transpose on the other side, just to see if you can figure that out. All right, so this brings an end to our discussion of Theorem 3.2. I hope you have enjoyed this. I will see you again for another video lecture on Section 3.3.